Okay, so good morning everybody, and before we start, I'll make a quick announcement. So everybody is especially stressed out about the final test. So unfortunately, we will have a final test, and it will be timed, and it will be virtual, and I'm not really going to proctor it. So it will be more or less open books. So whoever of you wanted to use a calculator on the test, that's good news for you. You can use the book. I'll ask you not to use the internet, and probably you'll have to sign some kind of statement that you're not cheating. But other than that, I'll just try to design the test to uh, to test your understanding and not how many formulas you memorized. Okay, so after saying that, let's start our first virtual class. And let's start by recalling the last formula we obtained, which I obtained in a great hurry. So here's a quick reminder. So we're talking about residue of of a function at infinity. And the way it was defined is that it was equal to minus the integral of 2 pi I over a contour such that f doesn't have any problems outside of this contour. And then we figured out that the residue at infinity, and this is where we stopped, is minus the residue at zero of this function. So we make our function bad kind of twice. So first of all, 1 over z means that we're moving the problematic point infinity to 0, and then this 1 over z square is kind of something that makes our life bad, because now our problematic point is at 0, and 1 over z square is kind of bad at 0. So let's do an example. And unfortunately, so this example is not so striking anymore. It would be nice to consider it on our last class. So let's integrate this function, and if you look a couple of pages back, you'll see that we've already integrated it around the same circle. So we already know the answer. The way we integrated it is that we realized that if our circle goes counterclockwise, that there are two poles, two residues, sorry, at z equal to 0 and at z equal to 1. And we know that integral of f of z dz is 2 pi I times the residue at 0 plus the residue at 1. And we actually computed these residues and computed the integral. So, okay, but now, however, we can notice that outside of this circle, f doesn't have any problems. And so we know, basically by definition, that the integral of f of z dz is minus 2 pi I times the residue at infinity. And what is the residue at infinity? So let's compute it. And the way we compute it is that we use this formula that you see in the top of the screen, which says that we actually need to look at this function. And what is this? So we have 1 over z squared, and then we have 5 divided by z minus 2. We have 1 over z times 1 over z minus 1. Alright, so let's do common denominators everywhere. We get 5 minus 2z. Here we have z, we have 1 over z, and we have 1 minus z over z. And then I forgot the 1 over z squared. I'll write it here. So these two fellows cancel out. This z goes to the top and cancels out with 1 over z squared a little bit. And so what we have is 5 minus 2z divided by z times 1 minus z. And now we need the residue of this fellow at infinity. Okay, at 0, sorry, we need the residue at 0. And the good thing is that this z helps us. So the only thing that we need to write as series is 1 divided by 1 over z. So let's see how it works. We have 5 minus 2z over z, which is fine, times 1 divided by 1 minus z. And this 1 divided by 1 minus z is easy to write as series. We have 1 plus z square plus z cube, so on. And we can now easily see how the residue, what is the residue? The residue comes from 5 over z times 1. So it will be 5 over z plus the good part. Let's see if I can, yep, I can scroll down. And so the residue of this function at 0 is 5. So the residue of the original function at infinity is minus 5, sorry, because we have a minus back here. There's a minus here. Okay, so the residue is minus 5, and the integral is minus 2 pi I times, I'll start over. So it's minus 2 pi I times minus 5, which is equal to 10 pi I. And this is exactly what we got before. So, lucky us, our computations, which were pretty nasty, got confirmed by this example. Okay, so let's maybe do some exercise. Let's compute some integral. So let's do what? Well, I'll just do one more example. I'll integrate 1 divided by 1 plus z square dz over the same circle is equal to 2. And we notice that this circle has two problematic points, I and minus I. The coordinates go somewhat like this. And now we have two choices, either to compute the residues at I and minus I, or to compute the residue at infinity. And I claim that the residue at infinity is way easier. So let's do the residue at infinity of our f is the same as minus residue at 0 of 1 over z square f of 1 over z. And what is 1 over z square f of 1 over z? It's 1 over z square times 1 divided by 1 plus 1 over z square. And this is just 1 divided by 1 plus z square. And now there are several ways to see that the residue is 0. One way to see this is that the residue makes sense only if our function has a problem at 0. But this function has no issue or no issues at 0. And so the residue is the same function, by the way, curiously. So the residue at 0 is 0, and so the integral is 0. Smiley face. Now, if you're curious, you can actually compute the residue at I and at minus I, and you'll see that these residues are actually not zeros, but they're like one is equal to minus another, and so when we add them, they'll cancel out and we'll get 0. Okay, now we move on, and Let me see, by the way, real quick if it shows me how much time I'm recording. No, it doesn't. I'll estimate then. Okay, so anyway, we will now discuss three types of what's called singular points. So what's a singular point? What a singular point? So z equal to z0 is singular if f is not analytic at z0 but analytic in, and I'm tired of writing formulas, so I'll just draw a picture. So here is z0, analytic in some circle around z0 except for z0. So we erase z0. And if this is the case, then we can expand f in Laurent series around z0. Okay, so we have something like this. We have the Taylor part plus the Laurent part. And it all depends on how long is the Laurent part. So case 1 is when the bad part is finite. That is starting somewhere and this will be our main case, by the way. Starting somewhere, we get like bm is equal to bm plus 1 is equal to so on is equal to 0. So this part doesn't go all the way to infinity. It goes just to some term and then it stops. So then z0 is called, and I used this word occasionally before, it's called a pole. This will be a really important word for us. Okay. Then case 2. Case 2, the bad part goes forever. And that's kind of a bad case. So then z0 is called, I'm trying to remember, an essential singularity. And then the best one is case 3 is no bad part. So, which means that f was in fact analytic at z0. So then there's no name for z0, then it's not actually a singular point. And it's called, then z equal to, then z0 is called, and this name tells you a lot, a removable singularity. Removable singularity. So removable means that we can just extend f, define it at z0. So you see, so this case 3 is basically a notational issue. So theoretically we could just state that the domain of f is this circle without z0, but if we write f as Laurent series and realize that there is no negative part, no bad part, then we can just define f at z0 to be a0 from here. and then we kind of remove this singularity. So the main thing is a pole. So we'll talk about poles a lot. So what does it mean that z equal to 0 is a pole? Well, it means this. It means that f has the good part, the Taylor part, and then we have what? We have b1 over z minus z0 plus b2 over z minus z0 square plus etc. plus, and then we go all the way to power m, and then it stops. I should confess that right here, I assume that it stops at bm, but whatever, if this term here is 0, then it doesn't hurt to write it. My point is that now I can factor this z minus z0 to the power m out, and then what will we get? We'll get the Taylor part of f times z minus z0 to the power m plus b1 z minus z0 to the power m minus 1 plus so on plus bm. And this thing in the parentheses is all analytic, even at z0, because, well, Taylor part times z minus z0 to the m is another Taylor type thing, and all these powers here are now non-negative. So this part is analytic. And so we get that our f is actually equal to phi of z divided by z minus z0 to the power m, and phi is analytic in a circle around inside the circle, yeah, around z0, including z0. So f has this really nice form that it's something analytic just divided by notice, by the way, that by an integer power of z minus z0. And so the main result, let's call it a theorem, is that then we can easily compute the residue, the residue of f at z0, and in fact it's the m minus first derivative of phi at z0 divided by m minus 1 factorial. This is true if m was bigger or equal to 2, and if m is equal to 1, we just get phi of z0. Well, if m is equal to 1, then it's kind of obvious, because if m is equal to 1, then let's look back here. Hope you see what I'm circling. So we look back here, and we see that phi is analytic, so phi of z, we cannot look there anymore, is some, let's call it alpha z, I won't have any denominators yet, some alpha 0 plus alpha 1 times z minus z0 plus so on, and I'm doing case m equal to 1. And so phi of z divided by z minus z0, which is f of z, is alpha 0 divided by z minus z0 plus alpha 1 plus blah blah blah. So that's the good part. Not good. Sorry, getting tired. Good part. And here is the residue. Okay, so if m is bigger or equal to 2, then we still have this same expansion for phi of z, except that now we need to divide by z minus 0 to the power m, so we'll have alpha 0 divided by z minus 0 to the power m, plus alpha 1 z minus z0 to the power m minus 1, plus blah blah blah, And what's going to happen when we have z minus z0? Well, right here we have like m minus 0, alpha 0, m minus 1, alpha 1. So here we'll have alpha m minus 1. Okay, so the residue at 0 of f is alpha m minus 1. And what's alpha m minus 1? Alpha m minus 1 is the m minus first term in the Taylor expansion of phi. And we know that the m minus first term is exactly equal to the m minus first derivative divided by m minus 1 factorial. Yep, at z0. So that's just, again, some kind of notational thing. But this is extremely useful. This is like super useful because we don't need a Taylor series anymore. Remember, I was advertising this way of computing the residue with writing just a Taylor series and then figuring out which coefficients we need, and then writing these coefficients in terms of the derivative. Well, here it is. So here's an example. Let's do 1 over z squared plus 1. And before I told you that the residue at infinity is easier. Well, now we can easily do residue at I, for example. So that's f of z. So what is it? So f of z is equal to 1 divided by z minus I times z plus I. Okay, so it's residue at I. Let's write it like this. 1 over z plus I divided by z minus I. This will be my phi. Phi is nice and analytic at I. And now we know that it's just going to be phi of I, which is 1 over 2 pi. 2 pi. Not 2 pi, 2i. And similarly, residue at minus I of f is this. Now, z minus I is a good guy. It's going to be minus 1 over 2i. So you see why I said that these residues will cancel out. This plus this is 0. So now we can go back. I keep telling you, like, go 3 pages back. Finally, I can go 3 pages back. 4 pages back. Here. Okay? Here, when we attacked this integral, I said that if you are curious enough to compute the residues at I and minus I, one will be minus another. And so it is. Alright. So let's do one more example. Let's do f equal to z plus 1 divided by z squared plus 9. So let's do residue at 3i, for example. Obviously, plus or minus 3i are problematic of f. So what do we have to separate? We have to separate z minus 3i. What's left? Z plus 1 divided by z minus z plus 3i. This is our phi. So we get 3i plus 1 divided by 6i. We can simplify this, but don't really care. I especially don't care because if we want to compute an integral, we'll need to multiply this by 2i, and I in the denominator will cancel out. Okay, let's do one more example. Let's do, for example, z cubed plus 2z, so that's also from the book. Let me do something funny here. Let's do z squared plus I cube. Z squared plus 1 cube, sorry. Okay, so I'll do residue at I. But first I'll write f like this, so I'll factor the denominator. I get z plus I cube times z minus I cube. So if I need the residue of f at I, I'll write it like this. And this is going to be my phi. So now my pole is not so simple anymore. I have 3 here. And so I know that our residue is the second derivative of phi at I divided by 2 factorial. Let's go several pages back. Here it is. Here is m minus 1. So if I have m here, I'll get m minus 1 here. So I need the second derivative. Well, now formally I need to differentiate. And I really don't want to, so I'll leave it as an exercise. That's really bad of me. These are devil horns. Looks more like a dizzy fox. But anyway, formally I need to differentiate phi twice. The book is more friendly. The book gives a way simpler phi. But if our life depends on this, we will do it, right? So taking second derivative of a fraction is not such a big deal. Okay. So, what else? So this is it for the residues, and now let's discuss an adjacent topic, which is called zeros of analytic functions. I have no idea why is it here and not earlier, but it is. Okay, so of analytic function. So let's now go back to analytic function and assume f is analytic around z equal to z0. Then f has Taylor series, Taylor expansion at z0, so no Laurent. And what does it mean that f has a 0? So at z0. So in particular, this implies that a0 is 0. Okay? So this already means that we can factor z minus z0 out. Okay, so in fact, if a0 is 0, we get this expansion, the 0th term disappears, and we can factor z minus z0 out and get this. So what does it mean that z0 has higher multiplicity? It means that if we divide by z minus z0, f is still 0. So for example, if let's say we divide, it's still analytic. Okay, so we can easily plug z equal to z0, and this is assume it's equal to 0. This will imply that a1 is 0. And what's a1? a1 is the first derivative. And then then z0 will be 0 of multiplicity at least 2. And so on. So z0 has multiplicity n if a0 equal to a1 equal to etc. equal to an minus 1 are zeros. Or this means that f of z0 is equal to f prime of z0 equal to so on equal to f n minus 1 of 0 is 0, and I should add, so multiplicity exactly n. It means that the nth coefficient is not 0 anymore. Otherwise, it would have multiplicity n plus 1. So this means that we can do our trick again. Before, in Laurent series, for the pole, we factored out 1 divided by z minus z0 to the power m. Now I can factor out z minus z0 to the power n, and what will be left is an plus 1 z minus z0 plus so on. And let's call this phi. So phi is first of all analytic, and phi of z0 is not 0. So it seems that I achieved nothing, but I actually achieved another incredibly important fact about analytic functions, that every 0 has integer multiplicity. So in 1D, there were this function like, let's say, third root of, not z, of x to the fifth. Or let's do, I don't know, x to the 10th. So what is this? Well, it's a function which is 0 at 0, its derivative is again 0 and 0, 0 at 0. And then maybe third derivative of, or whatever, one of the derivatives is not 0 at 0. But it's not only not 0 at 0, it actually doesn't exist at 0. If you start differentiating this function, you'll see that at some point x will go to the denominator. So 0 is kind of fractional multiplicity here. Has kind of fractional multiplicity. But this never happens with complex analytic functions. And that's actually a very important feature, so we can always factor out. And in fact, this is an important step towards proving our uniqueness theorem, which I probably won't prove now because proving it virtually is a disaster. But what is important here, important corollary, is that if f of z0 is 0, then f can't be 0 near z0. Sorry, probably heard a horrible sound. So why is that? Well, let's look here. If we are near z0, then this first factor is not 0. It's 0 only if z is equal to z0. And this first factor is also not 0, because if z is near z0, then all, like this term, are super small, so they become negligible, and an is not 0. So won't be equal to 0 near z0, which is really important. Okay, so we'll call it a day. I don't think you're watching this video before I'll live stream it, because I am recording it almost at midnight before the live stream. So anyway, if you're watching it live, okay, if you're not watching it live, sorry, and you want to watch it live, please feel free to ask questions. If you're watching it live, it's a wrong time to tell you about questions, but please feel free to send me emails, and I opened like sort of a forum on Canvas, so you can ask questions there. And see you on Wednesday. Bye bye.